All right, so these questions are a little different than what you just finished doing for homework, in that the questions that are assigned on page 113, questions 71, 73, 77, 79, are limiting reactant questions. And limiting reactant questions are a little different. The way that you recognize them is that when you look at the actual prompt, so you look at the word problem, instead of being given one numerical value in the question, they're going to give you two values. They'll give you two values for two different ingredients in the equation. I'm going to show you really quickly how we teach honors how to do this, and then I'm going to show you the way I want you to learn. If you had honors before and you know how to do it the old-fashioned way, reteach yourself. All right? So, limiting reactants, it's kind of like, say I have a recipe for a sandwich, and it takes 2 slices of bread to make a sandwich, and say 3 slices of cheese, and 1 piece of ham. All right, I love cheese. That's why this sandwich is disproportionately made of cheese. All right. So this is my recipe, and I decide to throw a party and invite my friends over, and I'm gonna make them my specialty, my 3 slices of cheese and 1 piece of ham sandwich. And I open my fridge and I find that I've got 8 pieces of bread, 6 pieces of cheese, and 1 piece of ham. And depending on how many sandwiches I can make that's gonna predicate how many friends I'm gonna invite over. Right?
I think I know where this is going.
Where's it going? Are you gonna say that I have no friends? All right. How many sandwiches can I make? 1. All right. So why? I don't have enough ham, right? I only have enough ham to make 1 sandwich. In this particular case, ham is your limiting reactant. The limiting reactant limits how much product you make. And it limits how much product you make because you run out of it. The other 2, you got plenty of. We call these other ones our excess reactants, because you got an abundance of those. All right, so let's think about what's in my refrigerator after my friend comes over and eats my pathetic sandwich. What do I have left? 6 pieces of bread, 3 pieces of cheese, no ham. All right? So that's the quantity of excess that's left over. This is the kind of math that you're going to do, but you're going to do it for chemicals. All right? So let's take a look at question number, 72? And let's read it. The questions in this particular section, I'm not keen on the publisher of this book, because now they've give you this reaction, right? And luckily it's balanced, so you don't have to do that work. But then, they forget to label these questions. There's 4 questions here, and they forget to label them A, B, C, D, right? And so they're going to ask you, which one is the limiting reactant? How many moles of this stuff form? How many moles of excess reactant are left over? That's they're getting kind of cheap there, right? They're getting kind of bold. They're trying to ask you, get 3-4 answers out of you, without giving you the common courtesy of labeling them A, B, C, and D. All right? I'm going to show you first how it's done the old-fashioned way, the long way, and then I'm going to show you a much quicker way to do it with something called a rice chart. And I know that the mix kind of got messed up around the part where I was explaining rice charts, so that's why I figured I'm better off re-recording this. The rice chart, it's really critical if you know how to do these problems the old-fashioned way, that you retrain yourself. The rice chart, I'm teaching it to you now because when we get to the equilibrium unit, which is 3 chapters long, everything is done with rice charts. And on the AP exam, they're going to give you rice charts that are half-filled, and you're going to have to finish completing them, so you need to know the structure. It's a perfect time to learn how to do them, okay? And the rice chart actually is going to allow you to answer every single one of the parts of this particular question in one fell swoop, rather than the old-fashioned way of doing it, which would take 4 or 5 fence posts, some numbers that you have to learn how to subtract from one another. Usually students subtract the wrong numbers together. It's much, much more straightforward, okay? It's kind of like how when I showed you how to do charts for those combustion analysis questions, how the chart helps you organize the information that you have, and it's just a matter of filling in the table to get to the final answer. Very similar notion. You're using the rice chart to organize the information for you so that you can come up with a solution. All right. So again, let's start old-fashioned method, and then I'll show you the newfangled method with the rice chart. And some books don't call them rice charts. They call them ice charts. I put the R in there to celebrate my Asian friends. No, I'm joking. I put the R in there to remind you to write down the reaction. Okay. All right. Okay, so anytime that you see two givens, right? So which reactant is a limiting reactant when 0.5 mole of aluminum hydroxide and 0.5 mole of H2SO4 are allowed to react? So when we used to teach this in honors, I would say to them, if you see one given, do one fence post. If you see two givens, guess how many fence posts you do? 2. 3, get out of town. All right, so if you have two givens, what you do using the old-fashioned method is you start one fence post with the first quantity they give you. It's 0.5 moles of AlOH3. You can't see that. Hang on, let me zoom it out real quick. And then the second fence post, that lighting is too much, isn't it? Hang on, let me turn the light down. How's the contrast?
I can't see it.
Well, you can now. Let the thing adjust. You do the second fence post with the second quantity that they give you. And essentially what you do, you pick one of these two products, and you set both of them up to solve for one of those two. And I'm going to pick water, just because, I know the molar mass of water. I've got it memorized. The other one I would have to actually calculate. And I'm trying to follow the law of least effort here. And I'm going to set both of them up to solve for some quantity of water. And given a choice, I'm going to solve it for moles of water, because I want to figure out who the limiting reactant is as quickly as I possibly can. So I'm going to try to make the smallest fence post I possibly can, because I want the math to go fast, because I really only have 1.2 minutes per multiple choice question on that test. All right? Okay, so you'll notice I'm starting with moles, and I've got both of them set to solve for the same substance, because we're going to come up with an answer, and I want to compare apples to apples. All right? So it has to be set up for the same substance. All right, so because I'm starting with moles, I'm allowed to just go ahead and go into the mole ratio. The mole ratio, according to the balanced chemical equation, is that you're going to need 2 moles of aluminum hydroxide to produce 6 moles of water for that first fence post. And then for the second fence post, you're going to produce 3 moles of H2SO4. You're going to consume that for every 6 moles of water you produce. So that cancels out. All right, so this is really easy math to do in our heads, right? Because this is basically 0.5 times 3. What's that? 1.5. And then this down here is 0.5 times 2, which is 1. All right. The smaller answer is your right answer. The top answer is extraneous. So you toss it. All right? You guys used to extraneous solutions in algebra? Yeah, okay. So basically, the only amount of water the maximum amount of water that you can make is 1 mole. And the ingredient that started that fence post, the H2SO4, that's your limiting reactant. All right? You can't make more than 1 mole of water because your H2SO4 runs out. So any calculation from that point on has to begin with that given for that substance. Okay? So if instead of being asked for how much water do you make, instead if they ask for how much aluminum sulfate you make, you would then do a third fence post, start it with that given, solve it for that material. Okay? Then if they want to know how much excess reactant is left over, you would do another fence post, starting with this, solving for the other substance, because this is the limiting reactant. The H2SO4 is limiting. The other substance on the left-hand side then is your excess reactant. You would solve it for the other thing and then subtract it from the given that you had from the beginning. So to answer this question now, you're up to 4 or 5 fence posts. All right? And it's not that it's difficult stuff to do, but if they gave you grams and they asked for grams, it could get lengthy and take up a lot of space and time that you just don't have the luxury for. All right? I wanted you to see this the long way just so that you can see where the numbers are coming from. All right? But there is a much better way of solving these particular problems. And that's going to be with a RICE chart. And so the first thing that we need to do is talk about what RICE stands for. All right? So what does RICE stand for? Reaction. So RICE is an acronym, right? Reaction. What's the I stand for? Input is good, but initial is more in line with what books use. And I'm going to change the acronym a little bit. Let's see if this lighting looks better. I think this is okay. All right. When we get to equilibrium, C is going to stand for change, but today I want you to call C coefficient. And when we get to equilibrium, E usually stands for equilibrium, but today we're going to call it end. So the end amount. Put some lines here. Okay, so let's write down the reaction that they give me in the question. So I've got 2 aluminum hydroxides plus 3 H2SO4s, 3 sulfuric acids, and I'm going to make aluminum sulfate plus H2O. 6 of them, as a matter of fact. All right. Okay, so I'm going to write some little steps here on the right. Let me move my book. This is kind of getting in the way. It's kind of hard to write on this. So the first thing that you're going to do is you're going to set up the R, I, and C lines of the chart. Okay? All right, so what does I stand for? Initial. These are the initial quantities. Now, what you should know about the RICE chart is that it only takes moles. It only works for moles. So if your givens are not in moles, you need to convert them to mole before you put them in the chart. If it only takes moles, it only spits out moles. All right? It will only accept moles, it will only give you moles. So if you want the answers in grams, in the final step, you'd have to convert them back to grams. But that's really simple to do. All right, so let's take a look at the initial quantities that they have here. What is the initial amount of aluminum hydroxide that they give me? They give me 0.500 moles of aluminum hydroxide. And they give 0.500 moles of sulfuric acid. All right, how much aluminum sulfate do I have present initially? By initial, I mean at time 0, before these things have reacted, have had a chance to react. There should be 0 of this and 0 of that. All right. Now, watch what I do with the coefficient line. I'm going to put some variables in here. Why am I subtracting on the left? Because they go away. Why am I adding on the right? Because they come to you, right? Reactants disappear as the reaction occurs. Products form. Did I finish filling out my R, my I, my C lines? Okay, my table's ready to go. Do something real quick. This light doesn't quite work contrast-wise. step 2, you have to identify the limiting reactant. Now I'm going to do it in a different color because this is just a little side calculation. It's not something that's going to be used to finish completing the rice chart per se. So I'm going to do it in red. All right, so at this stage, you're going to ID the limiting reactant. And the way that you do that is you take the first number, the first initial that you have, so the first given, so the given in the first column, and then you're going to multiply it by the mole ratio, and it's going to be the moles of the second substance over the moles of the first substance. You can't see that very well, but okay. So basically over here it's going to be 0.5 times 3 over 2. So that's a 3/2 in here. It's kind of small. All right. So what's 0.5 times 3/2? What's that? 0.75. So I take that product and I compare it to the neighbor. Is it bigger than or less than? Bigger than. And so I write an inequality symbol. Okay, so we'll write that down over here on the side. Okay, so you take the first given, you multiply it by the moles of the second substance over the moles of the first substance, compare that answer to the second given. And write an inequality. All right? What that inequality sign basically is an arrowhead. It's an arrowhead that points to the limiting reactant. So what's my limiting reactant? H2SO4. All right, it's usually this step right here that students have difficulty with, okay? The whole business of that part of just identifying the limiting reactant is what people normally struggle with. Okay? So that's the part that I want you to focus on when you're doing your problems is learning how to just take that first number, multiply it by second coefficient over the first coefficient, and taking that answer and comparing it to the next number in the second column. Okay? All right, well, now that I know who the limiting reactant is, now I can put a number in the E line. Now I got to finish filling out the E line. All right? What do you know about limiting reactants? What's the second definition? What happens to them? What happened to my slice of ham? It gets used up. And so at the bottom of the LR column, you're going to put in a 0. So step 3, enter 0 at bottom of LR column. All right, well, now that I have a completed column, I can write a very simple algebraic expression that will allow me to solve for x. All right? Because the way that this works is the I line plus the C line equals the E line. All right? So I plus C equals E. All right? So what I'm going to do is I'm going to write 0.500 minus 3x equals 0. Right? Or 3x is equal to 0.500. What's x? Is it 0.167? Yeah. X is 0.167. And that's in moles, so it's 0.167 moles. And now that I know what x is, I can now substitute it here, here, and there, and add. All right, so the E line here would be 0.500 minus 2 times 0.167. Here it would be 0 plus 1 times 0.167. And here it would be 0 plus 6 times 0.167. All right, so let's figure out what these numbers are. So 0.5 minus, I'm going to do this first column first, minus 2 times 0.167. I get 0.166 moles. So that's my final answer. Let me highlight it so you know what the final answers are. This one here is going to be 0.167. This is 0.166 simply because of rounding differences. And again, in mole. And this is 1.00 mole down here. Okay? So let's take a look at what we came up with a bunch of numbers. Let's take a look at what these numbers mean. All right? And let's take a look again at question 72 and see what they're asking. So the first part of the question is asking which reactant or which reagent is the limiting reactant. So which is the limiting? H2SO4, so sulfuric acid. They didn't ask this, but I'm going to ask it. Which one's the excess reactant? The ALOH3, the other thing that's on the left-hand side. These are excess reactants. So if you want, you could label them ER and LR. These over here, what do we call these things over here? They're called products. All right, part 2. How many moles of Al2SO43 can form under these conditions? Well, you look for Al2SO43 in the table. That answer would be whatever number you have at the end. So how much of this stuff do we make? 0.167 moles. All right? We went a step further than what the question asks. We went ahead and solved for the other substance, too. We told them how much water was made. They didn't ask for it, but we did it. Didn't take much to do it, right? We calculated how much water, too. And then in the last part, they ask how many moles of excess reactant are left over. Well, how much of excess is left over? So how much bread and cheese is left? Because I'm lonely and I only have one friend. 0.166 moles of aluminum hydroxide. So we tackled every last part of that particular question in one fell swoop with one quick calculation. So it was just simply a matter of figuring out what x was, because once you got x, the rest of it's easy. Okay? And this right here is 1,000 times more foolproof than doing it the old-fashioned way. All right? Doing it the old-fashioned way, you really have to know like what you're doing, because it requires doing like 3-4 fence posts, and then some of the answers from the fence posts you subtract from other numbers. It's figuring out what to subtract from one another that students always mess up. This is foolproof. All right? So this is just a really nice little method for doing stoichiometry questions. Now, what if instead of writing an inequality here, you'd gotten an equal sign? What does that mean? They both run out. So in those particular cases, you would put in a 0 for both. All right. That would be something that's perfectly stoichiometric. They would. All right. What if in the process of doing this math, you end up with a negative value down here for something? What'd you mess up? You didn't pick the right limiting reactant. If you ever see that, just erase your chart, do it again, and if you called this the limiting reactant the first time, just switch it. Switch it to the other substance. All right? Yeah, Sina?
So if that was a less than sign,
it'd be the other one that's limiting reactant. Okay. All right, let me do another one where they give you grams and they ask for grams so you can see how to incorporate that into the rice chart. It's still the same setup. We used to joke, we used to call them ricey charts because we'd put an extra I line and an extra E line for grams. But you don't have to necessarily. Let me just show you a quick setup. We'll do 74 and then we'll go migrate into the lab and finish our activity series lab. So question 74, same thing, but now they gave us the luxury of A, B, C, and D and marking things off for us. But it's the same relative concept here. They give you an equation, it's balanced. They ask if 1.50 grams of ammonia reacts with 2.75 grams of oxygen, what's the limiting reactant? How many grams of NO and H2O are formed? How many grams of excess reactant remain after the limiting reactant is completely consumed? And then in the final analysis, they want me to show that the calculations are consistent with the law of conservation of mass. Okay? We can answer every last one of those questions just with one chart. All right? So I'm going to do this to the side, and then I'll put it under the camera. I just need a little bit of room here. So, according to the steps I laid out for you, you start by just filling out the R, the I, and I'm going to put 2 I's and 2 E's. That's why we call them ricey. You know, 2 I's, 2 E's. Okay. We have to start by filling out the R, the I, and the C lines first before we even figure out who the limiting reactant is. All right, so in this question, they told me that I had 1.50 grams of ammonia and 2.75 grams of SO2. At time 0, how much product should I have in here? None. I haven't made any yet. Let me do the C line next, because that's kind of a no-brainer. So I subtract from the left, I add to the right. Instead of just putting an X, I put a 4X, 5X, 4X, 6X. What am I doing there? What am I incorporating there? The coefficients, right? This is where I'm doing that whole business of using the mole ratio. But what did I tell you about these charts? They only take moles. So that's why I put an extra line for I and an extra line for E. So I could do that conversion from grams to moles. So how do you go from grams to moles? Divide by the molar mass off the periodic table. All right, so the molar mass for ammonia is 17.04. And then the molar mass for SO2, I should have given myself a little bit more room. How much is sulfur? I can't see it from here. Did I mess up? Oh, 502. Yeah, I don't know my 5s from my S's. Oh, I know that mass. It's 32. So let's see, 1.50 divided by 17.04. I'm going to give it to 3 sig figs, so 0.0880 moles. And then 2.75 divided by 32 is 0.0859 moles. And this is still 0 moles and 0 moles. All right, so I'm now done filling in my I and my C lines. So step 2, figure out who the limiting reactant is. Okay, so how do I do that? I take this first number, and what do? Multiply it by 5 over 4. All right, so is that going to be bigger than, less than, or equal to 0.0859? Yeah, this is already larger than that, so if you multiply it by a number greater than 1, it's going to be greater than, right? You don't even really need to know what that actual product is. You just need to know that it's bigger than. All right? Okay, if it's bigger than, then who's your limiting reactant? That's your limiting reactant, which means that ammonia now is my excess reactant. That's my ER. And if I know that oxygen is my limiting reactant, now what am I allowed to do then? Put a 0 in for E in the E line, all right, and that's in moles, which then allows me to solve for X. So now I can write a mathematical expression with those numbers right there in that column because I have a completed column. So I'm going to write 0.0859 minus 5X equals 0. X is, let's see, 0.0172 moles. which now I'll go ahead and substitute here, there, and there, add, and figure out the end quantities. All right? So let me see, times 4 is 0.0687 mole for NO. Times 6 is going to be 0.103 mole for the water. And then this is going to be 0.0193 mole for the ammonia. Any questions so far? Here's the issue. They didn't want my answers in moles. They wanted it in grams. So now what? Multiply out. So basically you divide by molar masses to come into the table. You multiply by those same molar masses to come back out to grams out of the table. So here we would have to take this number, multiply it by 17.04. We would take this one and do nothing with it because 0 times whatever is still going to be 0. This one we multiply by 18.02. And then I would have, what's the mass of nitrogen monoxide? 14 plus 16 is 30.01. All right, so then this quantity here, 0.0193 times 17.04, I get 0.329 grams. This here I get 2.06 grams. Is that right? No, that can't be. Houston, we have a problem. Or do we? No, I think it's right. Hang on. This is 1.86 grams. Okay. Final question that they ask, and this is where I'm having a little bit of an issue. And I think you might have an issue too. Actually, I'm not having the issue. I know what the problem is. They want you to show that in your calculations the law of conservation of matter works. Does it? If I add this, does it add up to that? Okay, so what's the problem? What should you actually add?
Oh, the coefficient.
The masses at the beginning have to be equal to the masses at the end. So what were the masses at the beginning of this process? We had 1.50 grams of ammonia with 2.75 grams of O2. No. Okay. All right, well, what are the masses at the end? Well, what do we have at the end? We've got this that we made, and that's left over, right? So then you have to say 0.329 grams of the leftover plus the masses of the products that we made, right? So basically it's the masses of the reactants at the beginning have to equal the masses of everything at the end, all right? And hopefully those two things add up to the same thing. They do? Okay. So that's how you show the law of conservation of mass. What's that, Tina? These are the initial quantities for the ingredients that I started with. Yeah, these are the things that you started the fence post, the thing with. Okay. Basically, I have to show you, when you show this, go back to the recipe, the bread recipe. I have to show you that my sandwich plus the 6 leftovers and the 3 leftovers, that mass adds up to the original ingredients that I had in my fridge. Does that make sense now? Okay. So that's where you have to be really mindful of what numbers you pick, because I think the first gut instinct for most students is to take these numbers on the left and set them equal to the numbers on the right, and that's not quite how these work. Okay? All right, questions at this point? Fabulous. Let me stop the recording. We'll go in lab, and we'll take all of our things in